is yours.
Thanks everybody for coming. And first of all, before I go to the topic, I would like to thank my advisors, Professor Spacevich and Professor Greenstein, for their great help and support during the PhD process. And I'd also like to thank Professor Haimovich and Professor Ofinidis for becoming the committee member and give a lot of helpful suggestions and comments. And I also thank all of you guys for your support during the PhD process. I actually put a lot of acknowledgement to people collaborating in the PhD process in the PhD thesis on the first page acknowledgement part. So if you got a chance to say that, you probably will find your name. Today, I'm going to talk about the antenna and the synchronization design issues for the ultra-wideband system. By the way, the hand I'm here is an antenna for radio. So I'm going to start with an introduction of the definition of ultra-wideband system and a brief introduction of its history. And this talk will focus on three parts. The first part is the ultra-wideband antenna, and then the packet detection frame and frame synchronization issues. And there are reasons that why I focus on these three areas, and we will see them later. And I will introduce a MATLAB-based system simulator to show that there's a system type of platform that I can incorporate all the modules and the research done before into the system simulator and evaluate the performance from a system point of view. And finally, I will give the summary and conclusions. The definition of ultra-wideband system is that if the transmitted signal satisfies either the fractional bandwidth larger or equal than 20%, or the absolute bandwidth is larger or equal than 500 megahertz. If either of the criterion is satisfied, it is considered an ultra-wideband system. There's a claim that the wireless communication systems started as ultra-wideband. In 1900, Marconi sent Morse code across the Atlantic Ocean, and people later find in the document where the transmitted signal having a fractional bandwidth of around 25%. So therefore, it is considered ultra-wideband systems. And in the 1950s, the ultra-wideband technology was referred as impulse technology. And in 1973, G.F. Ross filed and was granted the first baseband pulse radio communication patent, which was widely regarded as the first ultra-wideband communication patent. Throughout the 1980s, ultra-wideband system has had three alternative names. They are baseband, carrier-free, or impulse. And in 1989, the term ultra-wideband was first officially used by the U.S. Department of Defense. And before this timeline, many applications were intended for military and undergoing confidential contracts. Throughout 1990s, Schwartz and Wen, both were at the University of Southern California at the time, generated a lot of publications which greatly promoted the proliferation of ultra-wideband technologies. And in 2002, FCC approved the commercialization of ultra-wideband devices under strict power spectral density emission limit, which is often regarded as FCC Mask. And currently, there are efforts going on try to standardize different technologies for ultra-wideband technologies. And two leading groups that are fighting with each other, one is led by the Freescale, which is a former spin-off of Motorola Corporation. They promote single-band type of CDMA-based ultra-wideband systems. The other group is led by TI and Intel. They were promoting the OFDM-based ultra-wideband technologies. And what's interesting is next. On January 17, 2006, the chair of this standard development committee declared the following. Finally, we reached an agreement that we do not agree with each other. So the 802.15.3 standard development activity disbanded. And they will let the market determine which technology is going to prevail. If you look at the intended applications for ultra-wideband devices, they're really focused on two areas in this distance versus throughput plot. The first area is the short distance, high throughput applications. For example, the wireless connections between multimedia devices, such as digital video camera and maybe digital projectors, the connection between projector and personal computers. The other focused area is with a relatively longer distance, but shorter throughput, lower throughput. These applications are majorly focused on sensor network applications. And this short distance, high throughput type of application are the focus of our research. If you look at the ultra-wideband system design challenges, which is mainly limited by the current FCC Mask, which is a power spectral density limit for, and here's an illustration of FCC Mask for indoor communication devices. And there are three major challenges. First of all, the power allowed to transmit by FCC is very low, and this is 41.5 dBm per megahertz. And in some cases, this allowable transmitted power turns into a 4 dB of received SNR at the receiver. So with this low SNR, many high SNR assumptions may not apply in the system designs. So we will see some of the results later. And the major UWB devices is going to operate from 3.1 to 10.7 gigahertz. And this means we have about 7.6 gigahertz of bandwidth to transmit. With this huge bandwidth available, many assumptions made for the narrowband systems and the results may not apply in the ultra-wideband case. And we will see some of the results for bandwidth challenges shortly. And also, the attractive of ultra-wideband was that the radio receiver can be realized with relatively low complexity. And we have to trade off between performance and complexity, which is always true for other narrowband communications, but it's especially important for ultra-wideband system, because with throughput goes high, and for the intended applications, we don't want a high-cost solution. And those are three challenges that we focus in the thesis. And in terms of approach to utilize this huge bandwidth, there are two major approaches as those guys are fighting before. The first group are promoting a single band approach, which means for each transmission of ultra-wideband devices, they utilize the whole available spectrum. And for this type of approach, the impulse technology can be used. And because such a huge bandwidth in the frequency domain, it translated into a very narrow pulse in the time domain. And the advantage of that is that the fine timing or multipath resolution can be realized by much narrow pulse in the time domain. And the challenges of this approach is that the antennas for such a wideband operation are not readily available, particularly for the low-cost and two-dimensional approach. And in order to satisfy this FCC mask, sufficient pulse shaping techniques has to be developed so that this mask is not violated. Therefore, the pulse shaping and antenna problems associated with this approach has to be addressed. And another approach is a multiband OFDM approach. And this approach divides the available spectrum into many subbands, and within each subband, the OFDM signaling is applied. And because of the property of OFDM system, it's easy to deal with multipaths due to its cyclic prefix properties. And also due to its multiband approach, we can achieve the flexible spectrum occupancy, means there might be different regulations in other parts of the world. We just knock off that subband and we're done. And the challenges associated with OFDM type of implementation is that there are more complexity and more cost associated with this implementation. And also, many operations of OFDM system were undergoing the assumption of high SNR, while for ultra-wideband systems, the low SNR challenges has to be addressed for this type of approach. And there are some implementations between those two approaches, such as a few band approaches, which is also adopted by one of the boxers, and which is not. I'm not going to address that. I'm going to focus on these two approaches, and the idea of this is dealing with the red part, dealing with the challengers, and they are exemplified by 3 blocks of work. For the ultra-wideband antennas, we design them for wide bandwidth. And there's also pulse shaping related topics in this part. And for the low SNR part, we find out there's a particular challenge for the packet detections. And for the low complexity, and we find out it's interesting to explore this problem, frame synchronization problems. So those are the focuses, and those are the challenges imposed by the two previous approaches. And that's the reason we focus on these 2 blocks of work. From now on, I'm going to talk about ultra-wideband antennas. Particularly, I'm going to talk about single-band ultra-wideband approaches, and particularly impulse technologies. If you look at the impulse type of ultra-wideband system, where the pulses, rather than carrier-based system, carrier-based signal is transmitted. This is the transmitted pulse, and this is the received pulse. Compared to the original pulse, and if you look at the time scale, there's significant dispersions in time scale. There's also significant oscillations in the received signal. So this is often referred as a rigging problem. Dispersion and rigging, if we look at in the frequency domain, the received signal has a much narrower spectrum than the transmitted spectrum. There's also a slightly shift of the center frequency due to the rigging problems. And these problems are the typical problems of using narrowband antenna, which is exampled using a dipole here for transmitting and receiving ultra-wideband signals. It's natural to use broadband to transmit ultra-wideband signals. Basically, there are 2 ideas of making antenna broadband. The first idea is to use combinations. If you look at the log periodical antenna, it is a combination of dipoles with different lengths. So with each dipole are resonating at a different frequency, the overall frequency response would be a linear combination of individual contributions. The second idea of making narrowband antennas broadband is to use smoothing. If we look at the biconical antenna, it forms a smooth geometry transition from the feeding point all the way to the radiation part. By this smooth geometry transition, it forms a smooth impedance transition property so that the pulse is minimally distorted from the feeding point to the radiation part. If we look at the first ultra-wideband radio communication patent, such an antenna was used in the system. It consists of 2 triangular mantle plates and forms a hole-like structure. And there's a claim in the patent document that there's a smooth geometry transition property and there's a smooth impedance transition property by this structure, so that the pulse is minimally distorted from the feed part to the radiation part. Now, these antennas could have potentially good performance for ultra-wideband system. The problems associated with them is that they have a 3-dimensional structure, which is not good for our intended application. We don't want a 3-dimensional antenna for some portable applications such as laptop. we want a two-dimensional solution with small size and low cost. Now, it suggests us to do something, though, based on the structure here. If we look at this antenna, it's called bow tie or butterfly antenna. And it can... Put it in my pocket. No, it's for video. It's fine now. If you look at this bow tie antenna, it can be simply considered we push this biconical antenna onto a two-dimensional plane. Or it can be considered that we put this two-mental triangular plate onto a plane. So it seems that we find something that's two-dimensional and also has a smooth geometry transition. It might have some interesting properties, and we will find out in a minute. Then we want to characterize this performance. And in order to do that, we composed 3 bow tie antennas with different expansion angles from 30, 60 to 90 degree. And we compare its performance to a half-wave dipole antenna. And the height of different antennas are scaled so that all of them are centered at the same frequency at 6 gigahertz. And the reason we choose 6, we will talk about shortly. And the software we use to characterize the performance is Agilent ADS and Remcom XFDTD. Now, if we look at the frequency responses of the set of bow ties and dipoles and compare to the signal spectrum, they are still too narrow to have any significant performance improvement. So it prompts us to do further. Now, if we flip over the previous two mental triangular mental plates, it forms a structure called diamond antenna, which is a time domain pattern. And use the idea of structure smoothing. We smooth the bottom edges of the upper triangular and the top edges of the lower triangular, and we realize something named rounded diamond antenna. And first of all, we want to find out whether this diamond antenna has a good performance. Second of all, we want to find out whether this rounding will help further in performance improvement. It turns out that the diamond antenna has a very broad bandwidth. And in addition to the diamond antenna performance, our rounded diamond has further bandwidth increment over the diamond antenna. And this bandwidth improvement will lead to a SNR gain, and we will show the number shortly.
Is there any reason why it's not symmetric?
Why this is not symmetric?
Is there should it be symmetric?
In fact, there's an approximation that this slope should be approximately like a linear thing, like a line. But here it's more smoothed. It's the reason is at this frequency, the antenna response is more like a derivative thing. But this has but the reason why it's not symmetric, I'm not sure. But typically people consider this as a line, that as a much smoothed application. So if you look at the antenna properties, it's almost like line here and smoothly rounding down. But why it's not symmetric, it's a question worth exploring further. Now we have a good antenna which has a wide bandwidth, and we want to find out what to transmit on the air. And if you look at the FCC Mask, which is illustrated here as a red line, it's a bunch of rectangulars in the frequency domain. So a bunch of rectangulars translate a bunch of sync functions to time domain. And so we derived something that's a combination of sinks, which we named them as FCC pulse. And the problem associated with sync pulse is it has long rigging tails, and we don't want that in the ultra-wideband systems. So we derived something called synthesized pulse that we achieved such a spectrum fitting in the frequency domain. And if we do some orthogonal expansion using some orthogonal basis, we could achieve a better fitting in terms of maximizing the energy. However, there are two problems associated with that. First thing is those energy maximization approach requires many bases to achieve a better approximation than this one. It's much more complicated. Second of all, this constraint optimization problem is not an already solved problem. It's much harder to do it. So we used a heuristically and practical approach. We used a linear combination of two second derivative Gaussian pulses. And we use 4 corners as a parameter to solve 4 parameters associated with this approximation approach. So the problem becomes much more tractable, and we think it's a practical solution in terms of we only have 2 basis functions to approximate the FCC spectrum. And now we have good antennas, and we also have a good pulse to transmit. How much we gain by using this good antenna and pulse combinations? And to answer this question, we need to know the separate transmit and receive responses of antennas. The first reason is that the transmit antenna response needs to be known so that the pulse on the air can satisfy the FCC mask. The FCC mask is a requirement of the radiated spectrum, not something that you received. Second of all, if we want to design the appropriate receive matched filter, we need to know the receive antenna response so that we can design the optimal maximum matched filter. However, in reality, we can only observe and measure on a pair basis. We have to have a receive antenna to measure the response of the transmit antenna. So we need a theoretical work on how to split the pair antenna response to obtain the individual response of transmit and receive antennas. So we did a lot of theoretical works on this, and here's the result. If we denote the pair transfer function as H and transmit only as H1, received antenna response only as H2, and the right way, or the ultra-wideband way to split the pair transfer function to obtain individual response is this. H1 should be proportional to j omega of H2, proportional to square root of j omega of H. And if we think about narrowband communications, omega is simply a constant. So a constant multiplied by a constant is nothing. So H is proportional to H2, proportional to square root of H. And this is a well-known way to split the narrowband pair transfer function to obtain the individual gains actually in narrowband systems. Now we have the right antenna, right pulse, and we have a theoretical way to characterize the individual antenna response. We can compare the SNR performance for different antenna and pulse combinations. And in order to do that, we first set out our reference, which is...
Maybe you want to define the transition functions, response functions.
Okay. Yeah. The transmit response is defined as a transmitting antenna. We have a voltage source and a transmit end. What actually out of that transmit antenna is the E field on the air. So the transmit response is defined as a ratio of the E field over the source voltage pulse. So in reverse, as a receive antenna, we have an electromagnetic wave on the air, and we converted that into a voltage on the load. So the receive response is defined as a ratio of the E field on the air divided by the load voltage. So it characterizes the performance of the individual antennas. And we have to notice, by definition, they don't have the same unit because one is E field divided by voltage, the other is voltage divided by E field. However, we want to compare its UWB shape distortion properties. Therefore, this comparison gives us meaningful ways to characterize their distortion properties. So now, in order to compare the performance of different antenna and pulse combinations, we select our ideal case, and which is also a hypothetical case. We have a perfect FCC pulse on the air, and we have an ideal antenna. This ideal antenna doesn't exist, but it's a hypothetical antenna with no distortion associated with this antenna. And next thing we do is we replace this ideal antenna with a rounded diamond. And the further thing we do is we replace this FCC pulse with our synthesized pulse. And the fourth case we compare is that we replace this diamond antenna with a half-wave dipole. And if we discuss all our previous research, and this is what we do. So we find out this rounded diamond antenna replace this ideal antenna, we lose 2.2 dB. And if we replace its pulse, we lose 4 dB. If we replace this antenna and this pulse, we lose 6.5 dB. If we don't do anything above, we almost lose 7.9 dB. Yeah. The reason, this is the incorrect way of characterizing how do we split the pair transfer function to obtain individual one. However, there are people still doing it in narrowband system. So we put a comparison of right splitting and the wrong splitting here. There's a differences between the way we split the antenna pair transfer function. And in some cases, it can be as high as 0.7 dB. So this is the right way. If you don't do it right, you get this number. So here's how much we gain. The rounded diamond antenna is 2.5 dB better than the half-wave dipole in terms of SNR. And the rounded diamond antenna plus the synthesized pulse provides 3.9 dB of a gain over we do nothing, just use the differentiated Gaussian and the half-wave dipole antenna. And we also find out by rounding that diamond antenna, we get 0.4 dB of a gain. This is what I emphasized in the previous slide, that if we don't split it right, there could be a 0.9 dB difference between the way we split the pair transfer function. Now we know that diamond antenna and round diamond antenna are good antennas, and we want to know further details about them. And particularly, we want to know the radiation patterns of the diamond antenna. And for ultra-wideband antennas, we also want to know whether the radiation pattern changes with frequency or not. And further, we want to find out what are the dominant factors affecting the radiation pattern. And the way we do it is to look at the current distributions on the diamond antenna. This current distribution is obtained by software IE3D version 8.0. And the current distributions are plotted for 3 GHz, 6 GHz, and 80 GHz. We have two observations for this current distributions. First of all, the currents concentrated mainly on the edges of the structure. And the current in the center of the structure is very cold. And the second observation is, as the frequency goes higher, this concentration effect becomes more and more significant. And also the current tends to concentrate more and more on the horizontal edges of the diamond structure. So this current distributions suggest us for the following model. This simplified model consists only of the edges of the diamond antenna. And the reason we do this is because it consists only edges. We can use analytical methods to predict the radiation patterns of this structure and compare it to the radiation patterns of this structure to find out whether they match well or not. And in order to analytically determine the radiation pattern of the simplified model, we use our linear elements-based models. We number the linear elements from 1 to 8, and each linear element is characterized by 4 parameters. It has a rotation angle, means element 1 is this angle, 5 is this angle. It has a length parameter, for example, 1, 5. It has a space shift factor, means the origin of this element and the origin of this element are located at different space of the coordinate system. And there's also a time shift factor, means the current starts from the origin, starts from the feed point, and propagates to the starting point of each element by a different phase. So by these 4 parameters, we can characterize the whole radiation structures of the simplified model by using linear combinations of contributions by individual elements. Here's the result. On the left side are the model predicted radiation patterns, and on the right side are the simulated radiation patterns. What we find out is at all 3 cases, they matched very well. They run from a donut shape at 3 gigahertz to a hot dog type of shape at 6 gigahertz, and then they give you a fortune cookie in the end at 80 gigahertz. So this result also tells us there's significant radiation pattern changes over ultra-wideband frequency, which is not a well-known result in the antenna community. And by the way, the antenna is oriented this way. We did some measurement for the diamond antennas. And for measurement convenience, we only use the half structure of the diamond antenna, put it onto a finite ground plane so that we don't have to create a balanced feed. That this is the dimension of the actual measurement that we did at Bell Labs in the anechoic chamber, Homedale, New Jersey. And on the background are the electromagnetic absorbing materials. And this is a platform. We mounted our antenna through a wood. And so this platform can rotate. We can measure and record the pattern parameters. Here is the result comparison of the simulated result and measured results. This represents measured elevation pattern, simulated elevation pattern, measured azimuth pattern, simulated azimuth pattern. And we can see there's a very good match between the measurement and the simulations. So we have a close measurement, a close match between the analysis, between the model and the simulation. We also have a good match between the simulation and measurements. Therefore, the model is indirectly verified. And we also find out that the radiation pattern significantly changes with frequency over the ultra-wideband bandwidth. And we find out that the edges of that diamond structure are the dominant factors affecting radiation patterns. And once we know that, we can probably achieve performance improvement by adjusting those important factors. For example, we find out the rounded diamond can achieve a wide bandwidth. And the next, we could probably find something named house antenna, which is named of the upper half structure of this structure. And if we think further about this house antenna, it is actually a generalized antenna of this category. The house antenna can be characterized by its V element and its H element. The diamond antenna is only a special case of the house antenna with this parameter, and this dipole antenna and square antenna are both special cases of the house antenna. And this tells us we can possibly, by adjusting these 2 parameters, to optimize this performance for a given application. Since we have 2 controlled parameters, and we can observe the performance so that the performance is optimized for a given application. And it turns out we can do this for the multiband OFDM ultra-wideband systems. The initial operation of the multiband OFDM operates from 3.168 gigahertz to 4.752 gigahertz. It has 3 subbands, and antenna has to cover all the 3 subbands for this operations. And the bandwidth here is defined, the S11 parameter is lower than -10 dB. And if you look at the bandwidth performance of the diamond antenna, it's actually wider than what's needed. And there are two problems associated with the diamond antenna. First of all, a too wide bandwidth is not necessary, and it might incur more noises because it can receive out-of-band noises. Second of all, we observe there are large variations within the operation band, and we find out there's a 3 dB rainfall associated with that diamond antenna, and we don't want that. We want a flat frequency response within this operation band. So we adjusted our V and H elements for the house antenna, and we achieved, this is the optimized blue, the one house antenna. It covers the sufficient band and has only 1 dB of ripple within the operation band. So this is an example that we can adjust V and H parameters to optimize for a given application.
Can I ask you a question?
Yeah.
If you look at the square antenna separately,
Yes.
and
It turns out
how is it?
it's like that. It has more variations within the band. And the bandwidth is actually narrow for the square antennas.
I'm asking because the house antenna looks like an array of a square with the triangular antenna. So could you analyze that by simple array theory?
It's possible.
Maybe using some
Go
calculus.
back to the house antenna. I think I see what you're saying. It's a rectangle with a diamond on top of it.
Yeah.
Right. So you
Think
could,
of it as
you could analyze each one and then add them
Yeah, with a face.
linearly. Right, with
Well,
the
exact. Actually, if you look at the counter distributions of the house antenna, it's like this. So this edge doesn't exist. So we can't analyze even an array, but we have to sort of eliminate this.
You can think of it as having that horizontal bar, except the current goes one direction for the rectangle and the other direction for the.
Yeah, we can do that. Yeah, we can do that. But what happens is, it's like this. So if you have a rectangular, it would be like that. There's nothing going on here. So we can't analyze using an array method, except there's no simple sort of a linear combination solution of a square and a triangular. We have to use that based on the counter distributions. It actually consists of like that. So it's still a house shape. So I did look at the counter distribution of this guy, and this guy. So, yeah, separately. And find out, even if you have more area of mantle, it doesn't help you. Now, we will look at the frequency-dependent radiation patterns of the diamond antenna. It means that if I'm located at a given direction in a space, I might have different gains because I have different radiation patterns. And now, what if I located at the same location of the space and I observe the impulse response of that location? Would that be different if because I'm located at different space or different angles of that space? So the problem is actually this. If you think about, we have a source antenna at the transmit end, and we have a radiated E field. And this E field is actually observed on different angles or different locations in the space. So it means the antenna has a transmit impulse response which might depend on this angle. So we want to find out whether this impulse response changes because I changed my location. The way we do it is that we define a metric, which is a correlation metric. We correlate the impulse response at the arbitrary location with the metric at this location. This location is theta equal to 90 degree, phi equal to 90 degree, and it's often referred as a bow-side impulse response. And we normalize this correlation metric by the energy of this bow-side pulse. And this is what we find. There's a large variation of this correlation metric, which means there's a large variation of impulse response based on different locations I am in. And However, this reflects both the radiation intensity, which is amplitude, and the shape difference for different directions. And if you look at only the shape differences regarding to different angles, we find out this change is modest. It's not that huge. Now, even if it's not huge, but here it's huge, that means based on different locations, I do have different impulse responses. How can I derive a... If we look at this in a link perspective, I have a received pulse, which is a convolution of the source pulse with the transmit impulse response and the receive impulse response. And if I have a local matched filter, V tau of t, and this is the SNR I'm going to have, since I have different pulses from different directions, based on communication theory, I have to match to each different pulses in order to have a maximum SNR. However, which is apparently not practical, I need to have a fixed local receive response so that I can maximize something. It turns out this something, we use the average SNR. We have a local fixed matched filter response, but we average this SNR over the probability density functions of all possible antenna orientations, which means all possible received waveforms. And we find there are some difficulties in manipulating this guy, and we used Cauchy-Short's inequality to maximize a lower bound of this metric. And we find out this problem is tractable. And the details I'm not going to show here. This is the result. Remember that we have a absolute sign here. In order to get rid of that absolute sign, we did some partitions. And this partition is negative projection partitions, and this projection is positive projections. And the solution of the optimal local matched filter is a linear combination of all incoming waveforms. They are decomposed into two sets. The first set belongs to the phi2, the second set belongs to the phi1. And for those falling into the negative correlation set, we have to put a minus sign there. And this lambda is simply a normalization coefficient so that we have a unit energy local response.
Okay, can I ask you about?
Yeah.
I was a little confused with that because both the phi1 and the phi2
Yeah.
depend on the solution.
Yes.
So when you actually find, so what you do, the way I read it was
Yeah.
that you assume a partition,
Yeah.
phi1 and phi2, and then you find the optimum solution.
Yes.
But when you now put that optimum solution into the constraint that it's positive over phi1, and
Yeah.
it doesn't necessarily satisfy.
Exactly. I have to verify if it's satisfied, it's following into the feasible set. If it's not in the feasible set.
That's because your optimization, your solution did not take that into account, that constraint into account. That it's positive over phi1 and negative over phi2.
In my actual computations, I actually do it in an iterative way. That I first pick an arbitrary partition. Then I use that partition to form my solution. And then replace the solution back into the equations.
Search over
Exactly.
phi1 and phi2.
Exactly. What happens is, in some cases, and actually in our case, this partition problem is very tractable. For example, for the cases where all the pairwise correlations are positive, one set is empty, the other set is a full set. And this has to be our case. So you don't even really have to search all possible or feasible sets. It happens to be one is a full set, the other is empty. But in general, this optimization problem has to search all the possible partitions and find out not only whether that partition is a valid set, but also you have to search all the possible partitions and find out the maximum one.
So at the end, you do have a solution that satisfies the constraints over
Yeah. You have to have one. There is definitely one that satisfies. Otherwise, the partition is not right. So the previous solution is a linear combination solution, which means the solution is a summation of all waveforms weighted by their relative probability of happening. And the disadvantage of that, we need to all the waveforms, and we need to know their associated probability density functions, and it's too complicated. And what we do this, we just select one of the incoming waveforms and use that as our matched filter response and find out which candidate is the best. And this is a simpler solution, and the performance is not bad. We will see in the next slide. Now, we use discrete candidates, and we discretize the space into a set of 1,296 candidates. And we calculate the metric values for each candidate and order them in ascending order. Clearly, this candidate produces the maximum metric value, and it's indexed 1,296. If you look at the performance of the linear combination solution and this candidate performance, they're very close. And it turns out this best candidate is a waveform received, and when transmit and receive diamond antennas are parallel and facing each other. It's like this. If the antenna are oriented like this, you get the best candidate.
Explain the 1,296. How can you have 1,296?
I have 6. I divided angles into 6 values from 15 to 90. There's 6 values of angle, but I have 6 angles. So, yeah, I have 4 set of angles: phi1, phi2, and theta 1, theta 2. So it's going to be 6 to the 4th, right? Now I wrap up the previous work on the antenna and pulse designs, and I'm going to focus on the next part on the low SNR challenges for packet detections, and particularly I'm going to talk about this guy. Well, the packet detection problems is that to detect whether there's an incoming packet or not, and give a cost estimate of the start of in a random access communication networks. Here's a brief illustration. Initially, there's no packet transmitting going on in the network. And when packet is starting to follow into the decision window of the receiver, the value of the decision window of the decision variable start to accumulate. When it reaches a certain threshold, it declares the packet has arrived. There's a packet going on in the network. It can be characterized as a hypothesis testing problem. Based on the received samples, we following a decision variable based on certain function and a window size of n, which composed of n samples. And we test the following hypothesis: the packet is present or not. And the performance metrics are probability of detection and probability of false alarm. There are many well-known methods for doing packet detections. For example, the energy detection or the average power method, which construct the decision variable as a power of the received samples. And the advantage of it is very simple. And the constraint of that is that the absolute threshold setting might yield different performance in different noise background. For example, the threshold set in a better noise situation might yield the worst performance in the worst noise environment. And the average power ratio method addresses the shortcomings of the previous method and use ratios rather than itself to characterize the packet detection problem. And the bad part of that about this method is that we find out the performance is not good. The correlation method is well known. We use the cross correlation of a local sequence with the received samples. And in order to do that, we have to have the local sequence embedded in the received signal so that we can generate meaningful correlations. And we find out this has a good performance. However, this assumes that the sequence embedded in the received signal is not severely distorted. If it's severely distorted, this would be generate very bad performance. In fact, in a multi-channel panel of ultra-wideband system, we find this method doesn't work. Well, here's the method of our focus. This method was invented by Schmidl and Cox. I think they were Stanford. Yeah. He is a faculty. He's a student. They form a decision variable based on also a ratio method. It's a relative method. The nominator is a correlation, but it's a self-correlation. Means it correlates itself based on the repetitive structures of the preambles. The denominator is a power. So the central idea of this method is that, first of all, it uses a ratio. Second of all, it uses self-correlation to combat signal distortions, based on the assumption that if the channel is static during the repetition period, the self-correlation will produce robust result against distortions, because the first half will be distorted the same as the second half. It turns out the method is good. However, in order to implement and analyze that method, we need a probability density function of that method. All the previous methods have readily available PDFs. For example, the average power is simply chi-square or non-central chi-square. Power ratio method is F ratio. Correlation method is Gaussian based on central limit theorem. However, for this method, the original authors approximate the distribution of that random variable as Gaussian distribution. The Gaussian assumption is simple and good for high SNR scenarios. And we find out it has degraded accuracy for low SNR, which is a typical operating environment for ultra-wideband systems. And we also find out in order to determine the probability of false alarm, we need to evaluate the random variable in a zero SNR scenario, which means there's nothing going on. I do not declare packages arrived, but there's a probability of false alarm. So I have to characterize that decision variable on this scenario. So all this points out that we need a new probability density function in order to apply this method for packet detection and also analyze its performance.
So you're saying that if you're going to the Schmidl and Cox method,
yeah,
and you just plug in noise, you cannot find the distribution of this thing?
I cannot find analytically.
The distribution of this random
Yeah,
variable?
yeah.
I don't know that for sure, but the other thing is that low SNR,
Yeah.
it's a bit problematic because at the end of the day, what we mean low SNR, of course, we mean average signal-to-noise ratio.
Yeah.
But whatever processing you do, you're going to end up doing it at some high signal-to-noise ratio. Otherwise, you're not going to get any packet detection or anything else.
Okay.
So you don't really need lowest. In other words, I'm not sure if it's correct to say that you need a different probability density function because you are working at low SNR. And I was looking for some charts to see at what probability of detection your, and the new method differs from the Gaussian approximation. I don't quite see that, but maybe as you go on, maybe you can.
Like, your probability false alarm, tell them about that,
Yeah. In that case, I will show the performance plot here. Here. If you look at the performance of zero SNR case, which we have to evaluate because we have to evaluate probability of false alarm. In that case, the Gaussian approximation completely collapsed. It does not apply. For example, the decision variable is 0. It's not 0 here. So, in a no noise case, it's not whether Gaussian is accurate or not. It's whether it's applied or not. But when SNR goes higher, there's starting to be a convergence process, so that actually you go to, in our case, you go to like 10 dB probably seeing good match between the Gaussian and
So this is SNR equal to 0. That
Yeah.
means that the
there's no signal. But you have to declare there's no signal. So there's a probability you declare there's signal, but there's actually not.
Okay,
The thing is, they made a Gaussian approximation, Schmidl and Cox, which is valid at high signal-to-noise ratio for their
I
metric.
understand, but when there is no, like in any hypothesis testing, you don't have to use the same PDF for both hypotheses. If it's noise only, you can use the noise only PDF.
Exactly. Well,
And you're saying that decision statistic does not have a closed form expression for the PDF when in the noise only hypothesis it seems
I think there is one.
because what you have a multiplication, right?
Hmm.
I mean it's a square basically.
Yeah,
So
but
that
it's
must be some kind of chi-square.
what happens is this. First of all, I was motivated by this problem because I first find out that in order to apply this method, I have to find a way to set the threshold, right? Otherwise, I don't have. This threshold can be set in two ways. You can base on the probability detection to find out the threshold, or you can base on probability false alarm. You can set the threshold, and then once you set the threshold, you can evaluate other performance. What happens is that if you don't have a probability density function which works for both cases, then you have to use a separate probability density function for either cases. And what?
This is, like in any detection problem, you use a Rayleigh distribution for the noise, a Rayleigh distribution for signal plus noise, and you set a threshold.
What happens in this case is that this PDF works in both cases. It's just parameterized by SNR.
You want, for some reason, you are looking for a PDF that works for both cases. You don't have to do that.
Well,
but
no, he's doing it because he wants to be able to operate at a low SNR, where you can't make that big a distinction between an SNR of 4 dB and a signal-to-noise ratio of 0. In both cases,
Yeah, I
in both
understand.
cases, the Gaussian approximation
Because
falls
like
down.
low SNR, if he can work in low SNR, it's better because he can do it positively.
But the decision statistic that you are using to determine whether you have a packet or not,
Mm-hmm.
whether you call this low SNR or not,
Mm-hmm.
that decision statistic is going to have two very distinct distributions. Otherwise, you're not going to find that packet, never find that packet.
Well, I think you were right when you said you can have a totally different distribution for the two hypotheses. There's no doubt about that.
That's clear,
It
yeah.
happens all the time. But he derived a PDF that is equally valid because, like he says, it's parameterized by the SNR. Turns out it's equally valid at either SNR equals 0 or 4 dB or 10 dB. So
If you look at the central and non-central, it's only parameterized by the central parameter, right? It turns out in this case, it's only parametered by one of the parameters. So that's why my motivation. It might be true they are completely different, but in this case, I can unify that.
But you could when you compare, you should maybe compare per Alex's comment.
Compare.
Use a different PDF for false alarm.
Yeah, there might exist one, but I don't know that one. So that's a problem.
Maybe you should look at it.
that probably does for the noise-only case.
I'm sure it's
Probably
pretty
doesn't-
actually, I think it's very simple.
Yeah.
I don't really think it's a big deal.
Yeah,
So I think we're discussing here
Yeah.
how to motivate how to motivate the fact that you're trying to use a single PDF.
Okay.
So it's really around.
Yeah, I think
we
the
can discuss that later. We don't
Yeah.
have to spend
but
too much
I
time.
think the current biggest motivation is the low SNR. Even
Well,
if you have
that
some.
one I think we should discuss later
Yeah.
as well. So let's not.
Okay.
Right, but what you should do for Alex is you should compare not with Gaussian, but you should compare with Gaussian approximation when you have
Mm-hmm.
for hypothesis H1 and
Okay.
the other one for H0. That's a fair comparison.
Yeah, I
So
can
you
do
have a
it.
gain there.
Yeah, I think in there's a signal case, I have gained low SNR. That is. Anyway, here is a PDF, the result of the PDF. That these guys are the quantities depending on the SNR so that, well, it looks complicated, but turns out it's fairly easy to use. If we have something like MATLAB or Mathematica, we just plug in this equation and set a k, and we find out when k is larger than 20, and this calculation can be very accurate. And those gamma function and hypergeometric functions are standard built-in functions of MATLAB, so it's fairly easy to use. Here comes the performance comparison of the low noise case and noise only case of the Gaussian approximation and our new approximation. Yeah, we will discuss that later.
I don't understand. What is this? What are these axes?
This is the value of the decision variable u, and this is the cumulative distribution functions.
Oh.
This actually is u smaller than u.
Okay, it doesn't
Yeah.
tell you, okay. What I'm interested to see
Mhm.
is the receiver operating curves,
Okay.
right?
Yeah.
And see there how this new PDF makes a difference or not. In other words, you're not interested in regions where the probability of detection is 0.1 or 0.2. You really
Okay.
have to work where the probability of detection is 0.8, 9, 95,
99 probably.
In that case, Schmidt and Cox were right that it doesn't really matter, because either you have enough SNR or the thing is not going to work anyway, so who cares?
I do have that performance comparisons. I do have that. Yeah, I have a curve there.
Do you have slides on that?
No, I don't have slides on that. Here's a summary of the this packet detection parts. That we have a new and accurate probability density function that enable this method to analyze for packet detection even at a low SNR. And we, in the thesis, we also compared 4 packet detection methods and their performances, which I do have the results. And we find out that the cross-correlation methods provide the best performance in the AWGN channel, while the SC methods provide robust results in all channels, by which we mean both the AWGN channel and the UWB multipath channel. And also, we find out this method gives a good trade-off between performance and signal processing complexity. Now I'm going to jump to the third topic. And the third topic is about frame synchronization of the OFDM ultra-wideband systems. Here is a system diagram of OFDM system. And this part is our focus. And I want to emphasize here, before I went in the stage, all the coarse synchronizations has been achieved, and only fine frame synchronization are needed for this stage. And the frame synchronization problem is this. If you look at one OFDM symbol, it has 3 parts. It has a prefix parts, it has a data sample parts, and it has a guard period. So the frame synchronization problem is that I should put the right frame into the FFT so that I can decode the data. And for example, this should be the right boundary between the prefix and data samples. So this should be the right frame I put into the FFT processing. Now, it turns out if I synchronize to T0 double prime, which means if I'm earlier, I'm going to be fine. The reason is that because there's a cycling prefix, the information missing here will be here. So there's actually an effective channel shifter, so that by channel estimation, I can estimate how much that I shift by this being this early. So synchronized earlier, I'm fine. However, if I synchronized late, which means I synchronized to T0 prime, I'm going to have a much bigger trouble. First of all, the information here is missing. When this feed into FFT, there will be a significant interchamber interference because all the subcarriers are no longer to be orthogonal. And in most cases, the guard period is much shorter than the prefix period. So there's a very high probability I might run into the next OFDM symbol, so that there's a possible inter-symbol interference problem. So there's an asymmetric effect. If I'm early, I'm fine. If I'm late, I'm in trouble. Yes?
You can restore orthogonality by doing a post fix.
Yes, I can do that. Yeah.
Right.
Yes, I can do that. That's one method to cheat the patient. So now it turns out my cases are almost always late. What happens for the previous synchronization strategies?
Could you explain, Alex, why you assume this?
Assume what?
This one without a post-fix?
That's a different approach to cheat the patient. So,
No, no,
and I mean, for ordinary OFDMs, you don't have postfix, right? The reason to do this, first of all, you sacrifice rate. Second of all, you
A little bit. I mean, we know how to design the prefix and the postfix. That you use. Of course, it's a bit of overhead.
yeah.
But I'm not convinced that you incur a cost either way. Whatever you do, it's going to be some cost involved. I
Yeah.
just pointed out that you can do.
Yeah,
it
there's
with
an
post-fix.
alternative solution. I agree with that.
But I think you're trying to focus on the spec, right?
Yes.
Okay.
So this spec, there's no postfix. That's one thing. Another thing is, if you put postfix here, you still have to have a guard thing. So
No, I agree. Well,
Yeah.
That's a good reason.
yeah.
If you wanna-
It turns out that we are always late. So because of the cross-correlation based, the cross-synchronization methods, the receiver tends to lock to the strongest path in a multipath environment. So if we look at the distributions of the strongest path for the multipath channels of UWB channels, and we look at this is the probability density of the, for example, if the strongest path is the first path, it has such a probability. If the strongest path is 10, it's such a probability. What we find out in this all three type of channel, that the probability that the first path is the strongest path is low. It's not high. So which means we synchronized not to the first path of the multipath channel. So we are always late. Now, the way to deal with that late synchronization is that I synchronize by doing time shift so that I can convert the late synchronization to earlier synchronizations. I compare the performance of a static shift, which means I determine offline an optimal parameter so that how much I shift, I should be fine. And I also derived as adaptive shifting scheme. And in order to keep the complexity low, I use symbol rate based algorithm, which means I compute something per symbol. And I can also use sample rate based algorithm. This processing has to be much faster than the symbol rate because I calculate the decision variable every sample, not every symbol. So here's the result for the channel model type 1. And this is based on different SNR, and this is the BER performance. And there are some interesting observations for this result. First of all, if I use a simple static time shifting method, in a low SNR region, I can achieve almost the same performance as the algorithm with the highest complexity. And it's even better than the symbol rate-based adaptive shifting method. However, as SNR goes higher, this static shift performance degrades. And there's some crossover point where the symbol rate adaptive shift is going to outperform the static shift. The reason is this. There's a trade-off between the synchronization accuracy and the channel estimation part. I omit the details for this part. If you're interested, you can find them in the thesis. So basically, we have results for all three channel types, and we compare their performance. And we find out because the ultra-wideband system often operates in a low SNR scenario, it's actually static shift is not a bad thing. So the most simple method is not a bad thing for ultra-wideband systems. You can do adaptive, you can do some symbol rate or sample rate. It's only going to help you in the high SNR scenario.
So maybe you want to tell us why you so much emphasize low SNR, because even with with a small with a low spectral mask, if you wait for a long enough time, you have enough SNR.
You have rate, right?
Right. So rate, right. What you're trying to say is that
You want high throughput at low SNR.
well, you don't. That's the focus that you're looking for. Right?
Yeah.
Because what you're saying is that the current spec and the current fight is for working at very short distances at very high rate.
Yeah, that's we have the throughput versus distance plot. That's the area that I'm working on.
So if you try to sort of emphasize, I'm trying to see how much I can study, I can understand better the work at low SNR, you're trying to see where are the limits in the sense of if I'd like to go at high throughput at short distances, how well can I do? But maybe Alex is pointing out that maybe you really have to wait for a long enough time to synchronize before you maybe send data at a very high rate.
Here's my point. When you look at Shannon and you see log 1 plus SNR,
Okay.
your SNR could be very low,
Mm-hmm.
and you're still going to get the rate.
Mm-hmm.
But when you do your processing,
Mm-hmm.
you have to build up your SNR
Mm-hmm.
to detect your symbols,
Okay.
because otherwise, nothing is going to work.
Yeah.
So building up, meaning
Uh-huh.
that you have to wait long enough, exactly like Petra was saying, or you have to use a strong enough code or something of that nature. There is processing gain involved in the system. So I'm not sure what you think you mean by saying low SNR, unless that SNR is 10 dB, in which case, okay, so this is conventional SNR. This is what you expect to see in order to do reasonable detection.
What happens in UWB, you have to work at 4 dB of SNR, not 10.
But then if you work at 4 dB of SNR, look at your curves, you're going to get a probability of error of
This is okay.
0.1.
This is okay in ultra-wideband, in pair applications. They are talking about 80% of packet error rate. So this is okay for them because they can do some ARQ or something like that. This is not okay for normal communications.
Okay.
But they have a spec that their receiver has to work at 4 dB of SNR, and their error rate is going to be a number.
So that would be useful, fine.
Yeah.
Useful to sort of put it up front that this is what you mean by low SNR. You mean
Yeah, for this
the
particular application that I'm considering, there's a number and there's a BR requirement. There's actually all the work here is based on that proposal. It's not something based on information theory. It's based on that proposal and what they require me to do this and do that. So.
Okay.
One could argue that's quite a bit.
Yeah, that's out of my capability.
No, okay, but it wasn't clear what your premise is.
Yeah, my assumption is that I'm working specifically for that application for that spec.
Alex is very right. We're sort of like working with him for a long time, and we're used to him sort of like focusing on details from the spec and then omitting them and putting them as a framework. But you really should emphasize, you should have had a slide which sort of details the spec.
I also don't,
Yeah.
I'm not sure that in the thesis it's quite explained like
Probably
that either.
the thesis is missing.
So I see low SNR, I'm thinking, Verdun's paper low SNR.
No. It's a completely different field. My low SNR is 4 dB. For me, that's low SNR. So, and that's specified by the spec.
Because again,
Even for the packet detection problem.
There is a lot of work in UWB for low SNR, but low as in average SNR.
Yeah.
Not bit error rate, but rather capacity, and it's a different type of.
Yeah,
loss.
those might be the guys sitting in the back. So, it's not me. I'm a sort of a practical guy following that spec. So that's why I come to this system simulator, because I want to stick to that practical, or you can argue that whether it's a good proposal or not, I'm sticking to that proposal and develop a simulator which strictly follow their specifications. Whether it's a good thing to do or not, it's not out of my scope. But anyway, that's what I did. And I programmed the transmitter and receiver. I have a graphic user interface that we can work with. And most of my thesis results are generated using a simulator. And here's a summary of the ideas of my thesis. I'm trying to identify the unique properties and deal with unique design considerations for the wideband, low power, and low complexity ultra-wideband systems. And the list of contributions are, we characterized the relationship between the transmitting and receiving properties of the same antenna. And we also derived an improved antenna design around a diamond which has a wider bandwidth. And we also proposed a linear element-based model that can predict the frequency-dependent radiation patterns of the diamond antenna. And we also quantified the direction-dependent antenna impulse responses and associated with the filter design problems. And we also had a new general antenna design, the house antenna, which potentially good for multiband OFDM operations. And we also have a synthesized pulse design, which is a linear combination of two second derivative Gaussian pulses and providing a close approximation to the FCC pulse. And we also quantified and compared the SNR performance of different antenna and pulse combinations. And we show that we had an improved probability density function that can help in analyzing and design practical packet detection schemes for low SNR links. And we also illustrated the performance advantage of the SC packet detection methods compared to other methods based on that new PDF. And we also have the performance and complexity trade-offs for the static and adaptive frame synchronization algorithms. And this is a simulator. We can wrap up all the work we did before. And this is a list of publications associated with the PhD thesis. And that's the end of the talk. I'd like to answer questions if there's more.